Next, we have a special friend online, Guyue Liu from Peking University, who will share her work on communication characters and optimizations of distributed large language model training. Guyue, please take it away. Thank you.
Hey, hello. Let me share my screen. Hello, can you see my screen?
Sorry, it's another screen. Yeah, you need to share.
Oh, okay. Let's see. Is this the right one? Hello,
Okay.
is this correct?
Good, thank you.
Okay. Yeah, thanks for the introduction and hello everyone. I'm Grace Liu from the Peking University and I apologize for not being in person and but I'm truly honored to have the opportunity to give the talk today. My topic today is communication characteristics and network and optimizations of distributed LLM training. So first, my background is from the networking side rather than the OS side, but I'm still working on the system in general. And I'm seeing like the networking is increasingly important for ML training. So in the past, when models were small enough to be trained on a single GPU, communication was not a concern. And however, as the data size grew larger, we adopt data parallel training techniques like the parameter server architecture to scale out training. And at that time, the communication requirements were relatively simple. But today, with even larger models and the data size, the training involves multiple parallel strategies such as data parallel, pipeline parallel, and so on. And the use these diverse strategies actually leads to the more complex communication patterns and higher traffic. So as a result, the networking is becoming more and more important for the training. And actually here is the traditional data center networking architecture designed for the general workloads. So at the host, we have both the GPUs and the CPUs, and these hosts are connected through some data center topology like the fat tree. And then the one topology links the different data centers to work together. And however, in the area of the AI workloads, this architecture actually faces the new challenges. And there are critical questions that we need to address in order to achieve the high performance, scalability, and availability. And here I'll list several questions our group is focusing on, including how should we design the transport protocol? How should we design the collective communication library? How should we design the topology? How should we schedule network flows? And finally, how should we locate and recover from the failures? And I believe for the AI networking, all these questions need to be re-answered compared to the previous network designed for the general workloads. And for today's talk, actually, I will focus on two of them. The first one is how should we design the collective communication library? And to answer this, we propose a system we call the HAT CCL, which is a high-performance collective communication library designed for the heterogeneous LLM training clusters. And the second question we try to answer is how should we design the topology? And we propose an infinite part, which is a data center scale high bandwidth domain architecture for LLM training. And so our both work are led by my students at Peking University, but we collaborated with the industry people, mainly to leverage their resources and the real traces. And I will start from the first one. And I will talk about the background, the challenges, and some high-level design, as well as some like evaluation results. So the background for this work is we actually like seeing the rapid advancement of the training actually driven two key trends for the training infrastructure. The first trend is the increasing size of the LM demands ever larger GPU clusters. And for example, for the state-of-the-art models have grown from the billions to trillions of parameters, and which requires the thousands of GPUs to meet the computation and memory requirements. And the second trend is that enterprises actually are increasingly adopting diverse GPUs from multiple vendors, and relying solely on a single vendor to build a homogeneous cluster is becoming increasingly impractical due to the factors such as cost efficiency, incremental upgrades, and the supply chain constraints. And this shift towards a multi-vendor heterogeneous cluster actually presents a promising opportunity to enhance the resource utilization and the cost effectiveness for LLM training. And however, realizing this potential hinge on the efficiency of the collective communication library, which orchestrates essential operations such as all reduce and all gather, since these operations are fundamental to parallelization strategies like the data parallelism and the tensor parallelism. And these are used to ensure the efficient synchronization and data exchange across the multiple GPUs. And actually, this figure shows the current collective communication architecture. And actually, we can see, unfortunately, this existing libraries are designed for the homogeneous environment and struggle to efficiently support the heterogeneous clusters. To make it more specific, actually, we look at the existing collective communication libraries. They can fall into the two categories. The first category we call the kernel-based approaches, and which includes the NC's Nico for the NVIDIA and the Rico for the AMD. Although they actually can achieve the good performance, but they are specialized for single vendor hardware products, and which are like the portability to run a heterogeneous environments. And the second category we call the CPU-centric approaches, and some representative architecture include OpenMPI and Glue, and they can move data across the heterogeneous hardware by copying the device data to the CPU. But clearly, this can introduce the high communication overheads and cannot achieve the desired communication efficiency. So as a result, existing solutions actually force a trade-off between the hardware efficiency and cross-vendor compatibility, limiting their usability for the heterogeneous clusters. And in this talk, actually, I want to talk about our solution, which we call HAT-CCL. It can achieve both high efficiency and the compatibility. And here is a high-level view of our architecture. And clearly, we're trying to adding a new layer on top of existing software stack, as I show here. And we want to provide unified APIs to existing collective communication libraries. And we aim to achieve three goals. First, we want to achieve the high-performance collective communication. Second, we want to do the portability across the heterogeneous hardware. And finally, we also want to incur minimal software adoption, only using the common functionalities that are widely supported by the various hardware vendors. So this vision looks very promising, but there are many challenges to achieve it. And here I list three of the key challenges we need to encounter. And the first one is the cross-vendor data transfer efficiency. And how can we eliminate the host-to-device memory copy overhead in current data transfer mechanism for the heterogeneous peers? And of course, we do not just rewrite everything for different vendors. This is not a practical solution. And the second challenge is for the heterogeneous collective algorithm model. How can we design a scalable modeling and algorithms search for the optimal collective algorithms? So for existing algorithms, they either only support very limited topologies such as ring-based topology or tree-based topology, or they have the scalability issues only limited to a few less than 10 nodes, which is not ideal for large-scale clusters. And thirdly, for the third challenge is how can we design a heterogeneous collective communication abstraction? And clearly for existing primitive design, they are just designed for the homogeneous clusters. And we want the primitives that are very efficient for the heterogeneous clusters. And long story short, we have a few ideas to address these challenges. The first one, we try to decouple the data and control passes to enable the device buffer RDMA to make the data transfer very efficient. And our second idea is we design a hierarchical primitive and algorithm to, to decouple the topology into intra-cluster and inter-cluster. And finally, we cluster the homogeneous devices and maximize the homogeneous communication. This can maximize the performance and leveraging the existing libraries. And next, let's look at our concrete design. And here is the architecture of our proposed framework. And at the top layer, we have the local primitives. And at the last layer, we have the vendor CCL adapters, which are the lightweight plugin for vendor-provided homogeneous collectives. And then on top of this, we have the local primitives, which are the device-level primitives for enabling the device buffer RDMA. And then we have the cluster-level primitives, and which models the cluster topology and the collective algorithm design space. And finally, at the top, we have the algorithm search engine, which can efficiently search for the optimal collective communicate algorithm for abstract topology. And some specific design. So for the first one, to make sure we have a high performance peer-to-peer transfer, we designed this device buffer RDMA. And our insight is we actually can decouple the control logic from the data path to enable the CPU-oriented device buffer RDMA across the heterogeneous devices, because we found the mean probability issue of the kernel-based approaches actually lies in the lack of the programming possibility for the control logic implemented with the device kernel functions. And the main communication of this, the second type of solution, the main communication overhead of it is a frequent and large host device memory copy. And for our solution instead, we use a CPU proxy for the RDMA control logic, including the resource management, posting to and pulling from the queue pairs, and where the data can remain on the devices. So it has a very fast data path as well as a very general control bus to be compatible with the existing libraries. And for the second one, our second design is synthesizing the heterogeneous collectives. Because the existing libraries support a very limited number of the predefined algorithms, such as the ring or tree algorithm, which is not always optimal for the arbitrary topologies given the asymmetry in the hardware capabilities. And we want to systematically search for the optimal collective algorithms. Then this requires modeling the algorithm design space with the optimization problem and optimizing a cost function of throughput and latency. Some existing solutions, such as CCL, is not very scalable, and even for a homogeneous cluster. So our goal is to make a scalable algorithm for the heterogeneous cluster. So we propose this cluster-level algorithm synthesis, and we represent a homogeneous cluster as a node in the graph, and then a cluster-level edge is a set of the physical connections across two different homogeneous clusters. On top of this general abstraction, we propose this topology extension, and we try to maximize the local homogeneous communication in globally heterogeneous clusters using a hierarchical topology abstraction. And we group hardware into the homogeneous subclusters by the vendor. And then at the subcluster level, we design the primitive abstraction that include both the intro and the inter-level subcluster operations. And this can leverage the efficient homogeneous communication implementations, as well as capturing the subcluster heterogeneity. And finally, to realize this algorithm, we need to propose the class-level primitives rather than just the rank-to-rank primitives. And we propose like 5 types of primitives, includes the cluster-to-cluster send and receive, and this concrete primitives here. And finally, I want to show some of our results. And actually, we have done extensive evaluation for this the entire design, including the efficiency of the heterogeneous device buffer RDMA transport, the performance of the heterogeneous collective communications, and the effectiveness of cluster level encoding and algorithm search. And finally, we have also done the end-to-end performance gain for the training. We have done this for 2 typical model training. And here I show some of the results. And actually, if we look at the data transfer performance, we compare to the existing solution, the Glue, and it actually can achieve 18 times higher bandwidth compared to it. And we have done several different like heterogeneous settings, and constantly we are better compared to, we are much better compared to Glue. And compared to the nickel ring homogeneous the operations, we can also achieve a better performance. And compared to the existing collective algorithm search, we actually can achieve like less than like 2 times lower cost compared to MSCCL, which is the state of the art for the collective algorithm search. And also we try to use a very small test bed with the heterogeneous hardware to do end-to-end training. We have trained like 2 small models, the 3B and 8B. And but even for this very small cluster, that the communication is not dominate. The computation, instead the computation is dominate. We achieve like very good performance, and we increase the end-to-end training time by the we achieve like 9% and 16% for each model. And I expect even for larger environments and with like more communication involved, then our framework could show even better performance.
Sorry, Guyue, I think there's an online question. You can. Can you see the online question in the chat box?
Oh yeah, I see it. Let me see. Oh, the question is what's the difference between the solver and the optimizer? So there are like 2 stages for our evaluation. I didn't go to the scales, and there are 2 stages, and we try to quantify the benefits of each stage. Okay. And to summarize the first work, and HCCL is actually, to the best of our knowledge, and it's the first fully device buffer-based heterogeneous collective communication library designed for the large-scale heterogeneous LLM training, and it can enable the efficient, scalable, and vendor-agnostic collective communication. And the key idea is we leverage the hierarchical primitive design and the very efficient algorithm search. And they also demonstrate a significant speed up in both the communication benchmarks and the real-world LLM training. Any questions so far? So this will end my first part, the first part of my talk. Okay, so then I will continue our second work, which we try to answer how should we design the topology, especially the highly bandwidth domain architecture. And our key metric here, we try to address the availability issue for existing HBD design. Okay, again, I will start with the background and then the design, and I will show some evaluation, very interesting evaluation results. So I will provide some backgrounds for the motivation that motivates our work. And training the LLMs within the AI data centers actually requires different parallel strategies, as I mentioned before. And but if we look at the communication characteristics of these parallel strategies, they are quite different. The first type is we call the communication intensive strategies, which includes the tensor parallel and expert parallel. And this has a higher communication, this incurs the high communication overhead and the higher network demands. And the second type we call the communication like not expensive but quite low, includes the DP, PP, CP, and recently the SP. And this has a lower communication overhead. So these are the network characteristics from the parallel strategies perspective. And then if we look at some like network topology design, we have two types of the topology. And the first one we call the data center network, or short for the DCN. This can provide typically 200 to 800 gigabits bandwidth, and this is used to handle those low communication patterns. And then we have the high bandwidth domain, which we call the HBD. This can provide the TP level bandwidth, which is crucial for the TP and EP, and some like typical fabric including NVIDIA NVL72 and Google TPU Wave4. But let me first introduce the existing HBD designs, which we try to categorize into three types. The first type we call the switch-centric HBD design. And the examples include NVIDIA DJX and JB200 and VL series. And this architecture actually utilizes switch chips to interconnect GPUs and providing the high performance any-to-any communication. And however, this switch-centric HBDs has several notable drawbacks. The first one is the extensive use of these hand bandwidth switch chips and links leads to significantly high interconnect costs for HBD, and which limits their scalability and contributes to the severe resource fragmentation. And for instance, when running a TP16 on NVL36, and despite no fault occurring, around like 13%, 30% of the GPUs remain unused, resulting in the wasted resources. And also there is a switch level for explosion radius, meaning that the failure of any individual switch can cause a bandwidth degradation for all GPUs connected to it. So to summarize, this type has a very high cost and has a very large fault explosion radius. And then let's look at the second type we call the GPU-centric HBDs. And some examples include SIP Ring and Google TPU Wave3 and Tesla Digital. And these HBDs rely on the direct GPU to GPU connections in ring and mesh-like topologies. And they face challenges with HBD level fault explosion radius, and a single node failure can actually degrade bandwidth for a group of adjacent nodes and compromise the entire topology. And for example, for SIP ring, one single GPU failure actually brings the ring and reforms the topology into a line. And the third type is we call the switch GPU hybrid HBDs. These HBDs actually combine the direct GPU to the GPU connections and the switch legs and kind of make a middle ground design. And the typical example here is a TPU Wave4 from Google. And it organizes TPUs into a queue, and they are connected through the centralized OCS-based switches, and it can scale up to the 4019 CPUs. And this has a moderate interconnection costs and scalability issues, and however, it still has several drawbacks. And the first one is the switch level for the explosion radius due to the OCS-based switch failure. And second, it also has a cube level for the explosion radius. Any node failure within the cube actually can cause a degradation in the communication performance across the entire cube. And to summarize the existing work, and we try to use this table. And from this table, actually, we can see the existing HBD architectures with fundamental limitations in scalability, interconnection cost, fault relevancy, and resource fragmentation. Then we kind of start from the first principle and to think about what could be an ideal HBD design. And to guide a better design, we actually analyze the existing training workloads and explore the three key contributors of an ideal HBD. And we found the first, as the cluster size and model scale increases, the optimal TP group size that maximizes FU also grows. And this highlights the importance of supporting a large and adaptable DP size for the HBD. So therefore, the HBD should be designed to offer both the low cost and the high scalability. Second, this is for the dense model. Second, we also explore the recent advances for the sparse models such as MPE. And due to the load imbalance issue for the MPE, this MOE models can still be efficient with the larger size of TP. So this is surprising. And this actually means the HBD doesn't need to be designed for the EP with the all-to-all communication. So instead, we should just optimize for the TP with the ring out reduce can meet the needs of the most training scenarios. And finally, of course, HBD should also have the high both relevancy and the high resource utilization. So based on these observations, we propose designing a large, adaptable, and cost-effective HBD architecture tailored for the ring-based TP communication and optimized for the LLM parallelism strategies with high force relevancy and scalability. And then let's look at our key design components. So based on this, following these design principles, we introduce we have the key insight. Actually, we can try to solve the fundamental limitations and by just unifying the connectivity and the dynamic switching and the transceiver level using the OCS. So because for previous solutions, they either just have the connectivity or the dynamic switching. And we found if we can unify both at the transceiver level, we can solve the issue. And as a result, we propose we call a transceiver-centric HBD. And at the high level, well, our idea is to embed the OCS within each transceiver to enable the reconfigurable point-to-multipoint connectivity. And with this idea, before I show in our concrete designs, we can look at this table to compare it with the existing architectures. It can achieve the high scalability, and it can support the ring out reduce, and it can achieve the lowest fault explosions, which is a node level failure explosion radius. And also, it doesn't involve any switch side failure problems, and the interconnection cost is very low, and I will tell you why. And also, the fragmentation is very low. So our design, we call it infinite pod, achieves a low cost, high scalability, high fault relevancy, and very few fragmentation, such has a very high resource utilization. And here I will show our three key designs. The first design we call the cipher-based OCS transceiver, which is a new hardware design. We call it OCS tracks. And the basic idea is we leverage the OCS and integrate it into a commercial transceiver. Our current implementation is based on the 800 kbps, and our key technique is using this silicon phonics technology, which can simplify the structure and reduce the cost and provides a lower power consumption. And this is by leveraging this hardware, we can really reduce the cost and increase the scalability. And with this OCS strengths, we try to design our topology. And for this hardware, it actually can provide connections with two GPUs, and it can provide three communication passes. The first one we call the cross-LAN loopback link, and which is the pass 3 showing this picture. And it can provide the direct GPU to GPU communication within a node. And then we also provide the dual external links, which we call the pass 1 and pass 2 in this figure. And it can connect to the different external nodes. And these three passes together are time division multiplex, which only one pass activates at any time. And the active pass can take the full GPU bandwidth, and also it achieves the sub 1 millisecond path switching latency. So that means when a failure occurs, we can quickly try to reduce reconnection topology. And on top of this basic hardware, we need to design our topology to achieve our goals. And so our key second design is the reconfigurable K-hop ring topology. And it enables nodes to connect to all other nodes within K-hops or fewer within the OCS chunks. And this figure actually illustrates the two-hop ring topology. And here the node 3 connects to node 1, node 2, node 4, and node 5. And the intro include two parts. First, the intro node topology can enable the dynamic construction of arbitrary size GPU rings at any location by activating the loopback path. And it can support the large and adaptable TP sizes. And for example, if N1 and N2 activated loopback path, and while N1's OCXTR2 and N2's another port can activate the external path. This can forming a ring between the GPUs. And by activating different passes at various locations, the ring of any sizes can be constructed. And the second, we also can provide the internode photo isolation mechanism. This can dynamically activate two external paths to bypass the faulty nodes. So this therefore can achieving a node level fault explosion radius. So for example, when node 2 fails, N1's OCS chunks 2 and N3's OCS chunks 1 can activate the external passes to their nearest neighbors, can forming a new ring and bypassing the failure node. Okay, so here I talked about the hardware part, the topology design, and but there's still one more thing we need to do, which is we still need the collaboration between the HBD at the DCN. As I mentioned before, for the internal architecture, it includes two parts of the fabric. One is the HBD, which mainly are used to connect the GPUs. And then we have the DCN fabric, which are connecting this HBD fabrics together. And the key part here is the placement algorithm actually influence the parallel traffic in the DCN. And so as shown in this figure, actually different placement mechanism on the left correlates to the cross TOR traffic, and the scheme on the right actually doesn't. And so if the TP traffic can frequently cross this top of the level switches, it can increase the risk of the congestion. So therefore, we need to minimize this cross traffic while maximizing GPU utilization. And we design algorithm with a two-phase solution at the deployment phase and runtime phase, try to minimize this cross the TOR traffic. Okay, and so our evaluation has been done on 4 node H100 GPUs, and we tested all existing representative HBD architectures, and also we try to use fault trace from the production with the 3K GPU cluster. And also we try to model different fault probability and to test our design. And by the way, for this fault trace is trace over 160 days. I won't go to the details of each figure. Basically, we try to compare our solution with existing HBD designs by using either a production trace or using our probability model. And the key metric here we try to measure is the wasted GPU, and we define it as the healthy GPUs, but cannot be used due to the fault propagation or fragmentation effects. And so we believe this metric is a good indicator of the HBDs for the relevancy. Actually, so in these figures, I can conclude our design actually achieves near zero GPU waste ratio, and which is over 1 order of magnitude lower compared to the NVL72 and the TPU-V4, which are really the state of art of the two representative HBD architectures. And also we compare the cost and power consumption against the solutions. And again, the InfiniBot can achieve the lowest cost, which is only 30% of the NVL72 and 63% of the TPU-V4. And also it achieves the lowest power. And to summarize, and for the InfiniBot is built on top of a new hardware design, which we call the OCS strengths, and also a reconfigurable K-hop ring topology and a new algorithm that to coordinate the traffic across the HBD and the DCN. And it can support the data center scale, dynamic TP group size, and the near ideal fault explosion radius. And our current sharing results by using the production trees and the models showing that it can achieve the near zero GPU with ratio and also a good cost reduction compared to the NVL and the TPU. Any questions? Okay, so to conclude my today's talk, and here I talked about our very recent work, actually both work are under submission. And so that's why I didn't show in the, I changed the name. And but the key idea is we try to answer the questions, how should we redesign the collective communication library and how should we design the topology? And our main vision is like in the area of AI networking really can be redesigned for the AI training or AI inference. And compared to previous network design, which only supports which the goal is to support the general workload, our job seems easier, just to support a specific workload. But actually, this is not that easier because for the AI workload, it really has a very different characteristic compared to the previous load we have seen before. And so under this way, we propose several questions we want to answer to really redefining the networking infrastructure from the top, from the down to the top. And there are more ongoing work in our group, and besides this topology and the collective communication library, which also including the transport protocol and the network flow scheduling and the failure recovery. And besides this work within a single data center, we also started looking at all these questions across different data centers because we envision like in the next, next generation of the training, we may not only need a single data center, but we really need multiple data centers working together to train a model or to do the inference. And for that case, how should we design the network to fit into that use case? And with that, I'd like to end my talk, and I'm happy to answer questions. By the way, here is my homepage and my email, and feel free to send me any questions. And if I don't have time to answer here.
Okay, thank you, Guyue. Any questions? Okay, sorry.
Hello, thank you for the great talk. I have two quick questions. So the first one is about the HET CCL. How is the scalability of it, right? So does it change compared to the previous work, or like is it better? And then another question is about the second work. I actually didn't understand. Maybe because I'm not very knowledgeable about your topic. What is a transceiver that you are doing, and to what is connected? If it is like a network card or like something else. Thank you.
Okay. Yeah. Thanks for the question. So for the first one, in terms of the scalability, especially for the heterogeneous clusters, yes, it's indeed improve its scalability. And I didn't put the result here. Let me see. I have the results. So here are the results. If you look at the state of art, which is MSCCL here, and when it beyond like this scale, and we try to restrict it to like 3 hours probably, and it was unable to find a solution just beyond these 3 hours. We just stop it, and so that's a representative of our scalability for this algorithm search. But for our case, we can do it much larger compared to it. So this helps answer the question. And for the scalability issue, for the transceiver,
Thank you.
let me show the results.
Okay, yes, thank you. Okay.
Let me show the result of the transceiver, sorry. To make it simple, I didn't put the internal details of the transceiver, but to make it simple, like original transceiver, if you can see like which connect two nodes together, the transceiver can just connect one node to one node, right? That means when the connected node was filled, the connection also filled. Both nodes could not work. But for our design, we actually found we should not only enable the we call the connectivity that connects one node to another node. So this is we call connectivity. And the key issue is when a failure occurs, we cannot switch this connectivity. And previously, when they try to achieve this issue, solve this issue, they will introduce a switch and use a switch to connect into this node as well. And when a failure occurs, the switch will switch the route into another route. But as we mentioned before, for this kind of switch-based architecture, it incurs the high cost and the large explosion radius. So our idea is we try to combine both this dynamic switching and the connectivity. And so we enable this dynamic switching, dynamic connectivity inside the transceiver. And so by using our transceiver, we not only need to connect into one node, we actually, if you look at this figure, we can connecting into two nodes. And these two nodes we call it one node to another multi-connectivity. And this multi-connectivity enables our dynamic switching. When one node fails, we can dynamically switch into another route. So this is the key idea behind this OCS transceiver.
Okay, thank you. Any first question? Okay.
Thank you for the interesting talk. I have one question regarding this CCL, regarding the cost function. So do you use some sort of heuristics to solve it, or is it, are you trying to find some optimal solution? That's the first question. And the second question is about what happens, if the topology changes. Let's say if there's some node fails or something happens, then how this communication, optimization, do you take into consideration, change of the topology as well?
Yeah, so essentially it's an optimal solution because essentially it's still we are trying to solving an optimization problem, and we encoded into SMT and using SMT encoders to solve this. And we try to do some small tricks to make it more scalable compared to the previous algorithms, but it's still an optimal solution. And for the second question, in terms of the failures, yeah, so unfortunately at this moment we still need to recompute this again using our solver to resolve it again. But this is actually a very interesting thought. How can we when a failure occurs, how can we try to search an optimal solution like faster than our current approach? I think that's actually a very interesting question to explore.
Last question. Okay.
So thank you very much for this super interesting talk. So again about this OCS transceiver. So it's a time division multiplexing. So my question is like, there's any protocol running between these transceivers to organize who will start transmission first, or how to schedule the transmission between different transceivers? Thanks.
Yes, so it's embedded into the hardware. Yeah, so I try to avoid the details about hardware design, but this kind of schedule was embedded into the hardware and then embedded into the transceiver.
Okay. Okay, we will step to the next phase. Okay, thank you, Guyue. Thank you again.
Thank you.
Okay, we will have a 15 minutes break, and we will back here for around 11:05. So let's join our group photo before the break. Thank you.